Hello students, good morning to all. Welcome to your beautiful channel Firjan. Today, see, today we discuss seventh video in second lesson electrostatic potential and capacitance. What is the concept now? Electrostatic potential energy. We discuss today electrostatic potential energy. Before going to this, we discuss what is electric field strength, electrostatic potential, and we discuss electrostatic potential energy. See, my name is Reddy. This is your beautiful channel Firjan. See, today we discuss electrostatic potential energy. See, electrostatic potential energy, electrostatic potential energy. Before that we discuss, see here, it is the point charge. Due to this or distance at this point, what is the electric field now? See, electric field equal to kq by r square, kq by r square. So electric field is vector quantity. What is the equation na? Kq by r square. See, electric field, for example here positive charge na away from the positive charge, negative charge na towards negative charge, it will act. See, electric field equal to kq by r square, kq by r square. What is the potential at this point or distance from the charge? What now here? K q by r. It is scalar quantity. See, we can write with the sign. For example, positive na positive we can write, negative na negative we can write. What is the electric potential na? V equal to kq by r. This electric potential is decreases in the direction of electric field. So what is electric field strength na? Kq by r square. Electric potential is kq by r. See what now? Electrostatic potential energy. So what about electrostatic potential energy due to this charge? See here, electrostatic potential energy is represented by u. This value is 0. Why it is 0 now? See here, due to this charge means single charge, potential energy is due. So means potential energy is not defined for single charges, single charge. See, potential energy, potential energy is not defined for single charge. It is not defined for single charge. So single charge we can't define the electrostatic potential energy. Potential energy is nothing but electrostatic potential energy or electric potential energy. Electric potential energy is not defined for single charge. See, electric field na kq by r square, electric potential na kq by r. Electrostatic potential energy is 0 for single charge. See, how we can define electrostatic potential energy na? It requires system of charges. It is defined for system of charges. Electrostatic potential energy, it is defined for system of charges. System of charges means minimum required two charges or more is there. So means it is defined for system of charges. Minimum require two charges or more also is there. So single charge we can't define the electrostatic potential energy. See here, for example, here we can take two configurations. See, this is one initial configuration. It is initial configuration. So it is final configuration. See, final configuration. See here, two charges is there. How to this one right now? Here it is initial configuration, final configuration. See, it has UF minus UI, that equal to negative of work done by electric force, or we can write positive of work done by external agent. Positive of work done by external agent. Why we can write now this one? See, here it is the configuration. Here two charges is there. See, in between them, see, some internal forces is there. So means due to this internal forces, either attraction or repulsion is takes place. Either attraction, repulsion is there, means definitely displaces. See, it will be attracting, so means, or repulsing, it moving from this place to this place. Yes, now some work is done. So work is done means how it will done? So electric force is there. Due to that, it will attract or repel. Because of that, some displacement is there. Work, displacement, force. Force and displacement is there, means definitely work is done. So that, so from this configuration to this configuration, it will changes. So that change in configuration, this configuration, potential, final potential, this configuration, initial potential. So means change in potential, we can write negative of work done by electric force or positive of work done by external agent. See, here in between them, some internal forces is there. What are internal forces? Electrostatic force is the internal force. Because of this internal force, either attraction or repulsion, it will changes its position here to here. What here? When force is acting, some displacement is there. Due to that, so what now? Here work is done. So that work is, for example, here for 20 joules or 30 joules is there, we can keep minus. So that work done by electric force, we call it as change in potential. In physics, electric potential energy is defined as change in potential equal to negative of work done by electric force or positive of work done by external agent. Why now here electric force? Now here it is internal forces. What now here? See, internal forces, internal force, it is a conservative force. Conservative force means the forces which do not depend on path, it's depend on only initial and final position. So whatever, see, for example, here this path to this point to this point, to we can go this path or this path or this path. In this case, see, first path, second path, third path. So is, see, that conservative forces does not depend on path, only depends on initial and final position. So such conservative forces, such forces we call it as conservative forces. What is the conservative force? Now here electrostatic force. Here in between them, electrostatic force is there. Because of electrostatic force, it will moving this direction, whatever different direction it will move, or attracting or repulsion is there. Due to that attraction or repulsion, it will changes, displaces from here to there. So that is final configuration, it is initial configuration. This change in configuration, in change in potential, final potential minus initial potential, that can be write it as negative of work done by electric force, or we can write positive of work done by external agent. Why we are writing positive of work done by external agent? Now here, see, while writing work done by external agent, we have one condition: provided change in kinetic energy is zero, there is no change in speed. It is an exact. So negative of work done by electric force is called as change in potential energy, or we can write positive of work done by external agent, means here we can write provided change in kinetic energy is zero. Provided change in kinetic energy is zero, or there is no change in speed. There is no change in speed. Change in speed. Why we are writing now here? See once. According to work energy theorem, we learn in 11th standard this one. See here, work energy theorem. What? According to what work energy theorem? Now work done by internal forces plus work done by external forces, external force equal to change in kinetic energy. It is the statement of work energy theorem. What is the statement here? Work done by internal forces plus work done by external forces equal to change in kinetic energy. What is the internal forces here? See, between the charges, internal forces is electrostatic force. Here, electrostatic force is the internal force. So it is actually we can write conservative force. Why we can write conservative? It will be depends on only initial and final position, does not depends on path. That's why it is internal force is conservative force. That conservative force, or we can write it as plus external force. So that equal to change in kinetic energy. See here, conservative force means here electrostatic force plus work done by external agent or external force. See, equal to change in potential energy is what? 0, provided change in kinetic energy is 0. So that's why we can write here 0. We write work done by external agent equal to negative of work done by electric force. That's why we can write here change in potential is nothing but negative of work done by electric force, or we can write positive of work done by external agent. It is the definition for electrostatic potential energy. How to write? Delta U. Delta U means change in potential equal to final potential minus initial potential, that equal to negative of work done by electric force, that equal to positive of work done by external agent. When we can write positive of work done by external agent, provided change in potential is 0, there is no change in speed, there is no change in speed. So it is the basic information about electrostatic potential energy. Now we discuss electrostatic potential energy for two charges. How to derive an equation? So that we can write now here. See electrostatic potential energy. See means electric potential energy. Electric potential energy for two charges. Two charges. What now here? See Q1, which are arranged at odd distance from the between them, or distance between them. For that, see here, what is the potential energy now? See K Q1 Q2 by R with sign, with sign. Positive is there, we can positive, negative is there, we can write negative. It is the equation of electric potential energy for two charges. What is the formula now here? U equal to K Q1 Q2 by R. It is scalar quantity. Scalar quantity. It is now work na, so it is scalar quantity. What is electrostatic potential energy na? Electrostatic potential energy is equal to negative of work done by electric force or positive of work done by external agent. For example, see here, this Q1 charge and Q2 charge we can arrange at all distance. For that, what we can do now, we consider so system of charges. So means Q1 and Q2 will be at infinity. Means how many charges at infinity, or number of charges at infinity. So that value, potential energy of that charges or system of charges, number of charges or quantity of charge, whatever that that potential energy is 0. Potential energy is 0. Potential for charges at infinity is 0. Yes, now it is the initial configuration or initial position. Initial configuration we can say. Why? Because here system of charges, so initial configuration is at infinity. At infinity, see these charges we can take and places here, arrange here. So for that, what now it is initial configuration, it is final configuration, it is final configuration. So change in this configuration, change in potential. See, we can write here, this is U initial, it is U final. U final minus U initial equal to negative of work done by electric force, or we can write positive of work done by external agent. This is the definition of electric potential energy. See, it is final, it is initial configuration. So here to here, how to arrange or distance from the or distance between them. So that arrangement we have to do some work. So by electric force, or we can write, that is we can take negative. So external agent now we can take positive. So that is called as change in potential, that we can write electrostatic potential energy. See here, for this one first we can take q1 charge, work done by external agent and bringing q1 charge from infinity to this point. So means q1 q1. So means here we can arrange q1. In this case, work done by external agent in bringing q1 charge, in bringing q1 charge, no work is done. Why now? Here no electric fields is there starting, so no electric potential is there, so that's why no work is done. So now just we can give small click, so it will come to here, it will place here q1. So that case, work done by external agent in bringing q1 charge from infinity to this configuration is 0. Yes na? So now we can do, so q1 q2, see here, work done by external agent in bringing q2 charge from infinity to here, we can arrange or distance from the first charge, or distance from the first charge. For that, here due to this q1 charge, some potential or electric field is there, it is positive now, it is positive, so repelled. So that's why we can do some work. For bringing here to here, we have to do some external work. So then only we can bring from q2 charge from here to here. So that work we can write here, work done by external agent in bringing q2 charge, that we can write here. See, work done by external agent in bringing q2 charge from infinity to required configuration, means or distance from the q1 charge. For arranging, we can do some work done by external agent, that work done by external agent bringing q2 equal to what we can write now, we can use electric potential. So means electric potential means, here see, for example, here one charge is there, q charge is placing at a point, a point. From here we have to do some work. So work done by external agent in bringing q charge from infinity to a point, we can write v a minus v infinity, that equal to work done by external agent in bringing charge from q to infinity to a on charge, we call it as electric potential. See, v infinity, potential at infinity is 0, so we can write v at a equal to work done by external agent in bringing charge from infinity to a by charge, we call it as electric potential. From this we can write work done by external agent, we can write where to where, infinity to a, that equal to v into q. V means here electric potential, electric potential. See, into which charge is bringing, so that charge we can write here. See here, see here what we can do, work done by external agent in bringing q2 charge and place or distance from the q1 charge. Due to q1 charge, some electric potential is developed here, that we can write here, work electric potential due to first charge into which charge is bringing here, q2, that we can write here. So means work done by external agent in bringing q2 charge, while bringing this one from infinity to this configuration, what happened here, some potential is developed here at all distance. Due to that potential, it will opposes, that's why we can do external work and place here this configuration we can arrange. So that work done by external agent in bringing q2 from infinity to this configuration equal to electric potential due to this charge into which charge is bringing, that one we can write. So V1 into Q2. What is the work done here? V1 into Q2. See, for this one, electrostatic potential energy for system of charges is equal to work done by external agent in bringing each charge from infinity to required configuration or this configuration. This configuration. What is the electrostatic potential energy for two charges means electrostatic potential energy for two charges is equal to work done by external agent in bringing each charge. Q1 charge we can arrange here, Q2 charge arrange here. So the total work done we call it as electrostatic potential energy. See that we can write here U final minus U initial, that equal to what we can write now here, positive of work done by external agent. See, work done by external agent in bringing Q1 from infinity to this one, this configuration, plus work done by external agent in bringing Q2 to this configuration or distance from the Q1. So means work done by external agent in bringing Q2, in bringing Q2. This sum total work done which is equal to electrostatic potential energy. So that we can write here delta U, change in potential. See, change in potential means final potential minus initial potential, that equal to work done by external agent in bringing Q1 charge from infinity to this configuration plus work done by external agent in bringing Q2 charge to this configuration or distance from the first charge. So that is here. See that we can write electrostatic potential energy, potential energy is equal to electrostatic potential energy for system of charges, for system of charges is equal to work done by external agent in bringing each charge, each charge from infinity to this configuration, this configuration. See, electrostatic potential energy for system of charges is equal to work done by external agent in bringing each charge, Q1 charge, what is the work done, Q2 charge, what is the work done, their work done sum we call it as change in potential energy or electrostatic potential energy, electrostatic potential energy. This is the main. See here, electrostatic potential energy for system of charges is equal to work done by external agent in bringing each charge from infinity to required configuration or this configuration. So that is called as electrostatic potential energy or electric potential energy. See here, work done by external agent bringing Q1. What is the work done? 0. Work done by external agent in bringing Q2 charge from infinity to R distance from the Q1. So that is work done by external agent in bringing Q2 charge equal to electric potential due to first charge into which charge we are bringing, Q2. So that one. See, V1 means here due to Q1, what is the potential now? K Q1 by R. What is the next bringing charge? Q2. So what is the work done by external agent in bringing Q2 charge from infinity to R distance from the Q1 is K Q1 by R into Q2. See, we can write here work done by external agent for bringing Q1 charge is 0 plus work done by external agent in bringing Q2 charge is K Q1 Q2 by R. Yes, na? So we can add this one. See here, we can add this one. We get the change in potential. So means U final minus U initial equal to first one 0, second one K 0 plus K Q1 Q2 by R. See what we get now here, U final minus U initial equal to k q1 q2 by r. See, u initial means where it is infinity. What is u infinity? See, 0. So means u final minus u infinity equal to k q1 q2 by r. So its value is 0 na. So means final potential energy. So means potential energy is equal to k q1 q2 by r. Means it is the electrostatic potential energy equation. So for two charges, see, u equal to k q1 q2 by r, we can write here u equal to k q1 q2 by r. It is the equation of electrostatic potential energy, k q1 q2 by r with sign. Why? Because it is scalar quantity, we can write with sign. With sign, it is the equation of electrostatic potential energy or electric potential energy for two charges. Yes na. So like this we can derive this one. First, what we can do now, here q1 q2 can be arranged at odd distance. For that we can select one another position, that is infinity. So why with this one? At infinity potential is 0. So these two charges will be at infinity. We are taking from infinity to this configuration. First one we can charge bringing, we can do keep here. Another one we can take and place r distance from the first one. So for arranging this we can do some work by external agent. So that total work done by external agent, which is equal to electrostatic potential energy for system of charges. That only right here, electrostatic potential energy for system of charges is equal to work done by external agent in bringing each charge from infinity to this configuration. That means that change in potential means here work electrostatic potential means this is initial configuration, final configuration. So final potential energy minus initial potential energy, that equal to positive of work done by external agent, or we can write negative of work done by electrostatic force. So we can take here positive of work done by external agent. Why? Because provided change in kinetic energy is 0. So work done by external agent in bringing q1 plus work done by external agent in bringing q2. So that total we call it as change in potential. That is for first charge bringing work done is 0, second charge is k q1 q2 by r. How it will get na? Work done by external agent equal to electric potential into charge. Which charge is bringing, that we can write. What is the electric potential? We write here due to first charge. What is the charge here? First one. So later we are placing q2. So due to this charge, here some potential is developed. That potential into this charge we call it as work done by external agent in bringing q2. Work done by external agent in bringing q2 means product of electric potential due to this charge at this position, what is that one, into this charge. So that is v1 into q. V1 means here some develops some electric potential due to first charge, that potential into what is the charge we are bringing from infinity to here, q2 charge, that q2. So means potential into charge. So that is k q1 by r. It is for due to this q1 charge, q2 na this one. So that is k q1 q2 by r. This is the work done in bringing q2 charge from infinity to this configuration. This charge bringing 0 work done. This charge k q1 q2 by r, that only I write here 0 plus k q1 q2 by r. So we can add now here k q1 q2 by r, u final minus u initial. U initial is 0. Why? Because potential at 0 infinity is 0. U final is u initial is 0. So this value 0, u f equal to k q1 q2 by r, u equal to k q1 q2 by r. With the sign we can write. Why not? Electrostatic potential energies scalar quantity. That's why we can write with the sign we can write. Yes na. So this is the derivation and definition of electrostatic potential energy. According to this we can do some problems. First we can do board level problems later. So JEE NEET level problems we can do. See here, what now here, see, electrostatic potential energy. What is the formula na? U equal to K Q1 Q2 by R. See what is the first problem now here. See, we can take three charges which are equal in magnitude. These are arranged at vertices of equilateral triangle. See, this is the equilateral triangle. It is A, B, C. Charges will be arranged. Each charge will be arranged at each vertex. One will be arranged with each vertex. We want to find out what is the potential energy for this system. That we find the potential energy, means electric potential energy for arranging each charge each charge on or at vertices of equilateral triangle. What is the potential energy is required for arranging each charge at this one? See, for that what we can select now? First, infinite one position, one configuration. It is the final configuration. So infinite configuration, first from infinite configuration, for example, here is there q1, q2, q3 is there. For example, this will be first one. First charge we can place here A position, no work done. Why? Because there is no other electric fields or potential is there. For placing second one, arranging here, we have to do some work by external agent. Why? Because due to this here some potential is developed. So this potential opposes the q2 charge. That's why we can do some work, external work, and arrange here. So that work is actually, so work now potential into charge. Which charge is bringing that charge, and potential what we can use now? This potential. Due to this charge, what is the potential developed here? That we can use. For example, see, for arranging q2 charge, what is the work done we can use now? Work done by external agent in bringing q2 charge and arrange at C position now. See what now here? Potential due to this one. So means A into which charge is bringing q2. So that means work done by external agent in bringing q2, that equal to k q1 q2 by R. Why we can write now here? So due to potential A, due to charge at A, some potential is developed at C. So that is k q1 by R into charge q2. This one. See, for example, q3 arranging. For arranging q3 charge, we can write, see, work done by, for arranging q3 charge, work done by external agent arranging q3 at B position. What now here? Due to this some potential, due to this some potential. That's why two works is done. So what now here? Work done by external agent due to this one, some potential is there. That's why we can write due to this potential into this charge, potential into this charge. So we can write here, see, k q1 q3 by R. Here distance is R. Now we can take R. Here distance is R. K due to this some potential developed here, that potential into this charge means k q1 q3 by R. See, plus k q2 q3 by R. Why now here? Due to this also some potential developed here, that potential into this charge. So this is the work done by external agent in bringing q3 charge from infinity to this configuration. So what is the now here? Potential due to potential energy, means work, or we can say that work done by external agent due to this one. So k q1 q3 by R due to this k q2 q3 by R. That we can write here potential energy. So between these two, potential energy between these two, that we can add. So totally add now. So work done by external agent in bringing q1 charge, bringing q2 charge, bringing q3 charge. So what we can write now here? Change in potential equal to work done by external agent in bringing q1 charge, work done by external agent in bringing q1 charge, plus work done by external agent in bringing q2 charge, work done by external agent in bringing q3 charge. See, Work done by external agent in bringing Q1 charge is 0. I write here 0. So means that we can write here UF minus UI. So that is first one is 0. Second one, work done by external agent in bringing Q2 charge is VA into Q2. VA means this one. So means KQ1 by R. See, I write here KQ1 Q2 by R plus work done by external agent in bringing Q3 charge. What KQ1 Q3 by R1? K Q1 Q3 by R1 plus K Q2 Q3 by R1. See what we get now here, its value is 0. Why? Because at infinity. So U equal to what? K Q1 Q2 by R plus K Q1 Q3 by R plus K Q2 Q3 by R. Yes, na? This is the formula for electric potential energy for arranging Q1, Q2, Q3 charges at vertices of equilateral triangle. See what we can do now. First, Q1 charge we can arrange here. So Q2 charge we can arrange here. For that we have to do some work. So what is the work now? Actually, work done by external agent equal to potential into charge. So here arranging due to this some potential here, that potential into this charge that I write. So for arranging this here, two potential is there. Due to this potential, due to this one potential is there. So that's why we have two work done is there. Due to this one work done, due to this one work done. Due to this work done is work K Q1, this charge is Q3 by R. Due to this is some work done is there, that is K Q2 Q3 by R. So this all we can add. So means Q1, Q2, Q3. So we can add what we get now here, work done by external agent in bringing Q1, work done by external agent in bringing Q2, work done by external agent in bringing Q3. Q1 is 0, Q2 is this one, Q3 is this one. We can all add all, we get the this formula. This we can write here generally, we can write it is U12 we can write. Why? Because potential energy for 1 and 2 charges. So we can write this one, potential energy for 1 and 3. Why? Because what is the potential energy formula? K Q1 Q2 by R. Here K Q1 Q2 by R means potential energy for between these two charges. Next now Q1 Q3 is there. Q1 is this one, Q3 this one. See here U13 we can write plus here Q2 Q3 is there. So we can write U1 sorry 2 3 we can write. This is the formula for potential electric potential energy for arranging three charges at each vertices of the equilateral triangle. See we can write now directly. See U12, what is the potential energy between these two? Q square by what is the distance R. See K Q square by R plus U13 this one. See K Q square by R. Here also same. See why? Because same charges na same magnitude. K Q square by R. See we can write U equal to 3K Q square by R. It is the potential energy for arranging each charge at vertices of the equilateral triangle. Yes na? What is the potential energy for arranging each charge at vertices of the triangle na? 3K square by R. 3K square by R. Yes na? See next one. Next problem is, what is the potential energy for arranging four charges at each vertex of the square? We can arrange now square. See I write now here C square. Now this is the square. Yes, na? In this one we can arrange charges. Here one charge Q, here one charge Q, here Q, here Q. It is A position, B position, C and D position. This distance is A, this distance A, this distance A, this distance A. See here, find the potential energy for arranging each charge at vertices of square. Vertices of square. So that we find out. First what we can do, this one we can arrange. So now, so potential energy. See for arranging this one, no work. Why? Because first charge no electric field is there. Work done by external agent in arranging q1, for example we can write q1, so no external work. So for arranging this, here is there potential is developed due to this one, that's why we can write work done by external agent for arranging q2 charge, q2 charge, so q2 charge. So that is next, for arranging this charge due to this one potential developed here, due to this one potential developed here, definitely we have two work done is there, due to this work done, due to this work done, due to this means work done by external agent due to q1. So means q1 means here for arranging q3 we are arranging q3, work done by external agent in bringing q3 a place at c, due to that, due to this one work done, due to this work done, see I write here 2, see work done by external agent arranging q3, two works is there, due to this one, due to this one. See next, for arranging this one, here see, due to this one work, due to this one work, and due to this one work, so three works is there. See now here how many now here, due to this one work, due to this one work, due to this one work. So why? Because due to this potential develop here, due to this potential develop here, due to this potential develop here, that's why we can write work done by external agent, external agent arranging q3 q4 here, due to this I write q3 one work done plus work done by external agent due to this one q2, due to this one also is there, so work done by external agent in arranging due to q1 also. See how many is there here, so this work done is 0. Why? Because initially, so initially no work is done, so now why no electric fields is there, that's why no work. See I write here total potential energy equal to work done by external agent in arranging q2, this is due to this some work done, so that's why we can write here that is u12 plus due to q3 arranging q3 na, due to this one, due to this one, so due to this one I write u13 plus due to this one u23. Next see for arranging this one, see due to this one potential, so that is u here 4, here is 3, 3 4 plus due to this one, so 1 4 u14 due to this one u24. See here totally how many, 1 2 3 4 5 6 potentials is there, 6 work done is there, 6 electric potentials is there. What is the formula for potential energy? U k q1 q2 by r. So it is one potential energy due to, for arranging this one potential energy, this one potential energy, this one potential energy, this one potential energy, this two one potential energy, here potential. So that all arrangements, how many configurations is there, for that we have one formula, so that is how many charges we are arranging on vertices, 4 charges and 4 vertices. How many combinations, 2 2 will be one combination, these two, these two, these two, these two, and these two and these two. See for that we can write how many charges now in each combination, 2, total charges 4, total charges 4, each configuration how many charges, 2, 4 c2, that equal to 4 factorial by 2 factorial into 4 minus 2. See here I write again, see here 4 means number of charges is there, total number of charges, each configuration how many charges, 2, 4 c2, 4 factorial by 2 factorial into 4 minus 2, so we can get. So what is the answer now here, 4 into 3 into 2 into 1 by here 2 factorial means 2 into 1, here 2 into 1, yes na, so 2 2 are 4, 4 cancel, but here 6 configurations, that only we are getting here u12, u13 13, u23, u34, u14 and u24, these are the configurations we are getting. How many na, in between them one potential energy, potential energy, potential energy, potential energy, this diagonals, how many totally, 6. Here u12 means I write here k q square by a, u12 in between them potential energy, u13 13, here now what is the distance now here, root 2 into a, that's why we can write here k q square by root 2a plus u 2 3 this one distance is a, so k q square by a plus u 3 4 here potential energy is k q square by a plus u here potential energy is u sorry k q square by a, see u this one, see here k q square by root 2a, see all have k q square by a, we common here u equal to what, k q square by a, we can write here, here 1 by root 2, 1 plus 1 by root 2, 1 plus 1 plus 1, see 1 plus 1 plus 1 plus 1 by root 2, see here, here we can write 1 2 3 4 4, right here u equal to k q square by a into 4 plus 2 by root 2, see here 1 2 3 4 plus 1 by root 2 1 by root 2 na 2 by root 2, u equal to k q square by a into 4 plus this 2 can be write it as root 2 into root 2 by root 2, 2 2 cancel, what we get now here u equal to k q square by a into 4 plus root 2. This is the potential energy required for arranging 4 charges at each vertex of the square, each vertex of the square. So what now here, for finding potential energy for system of charges now, simply we can write, you can take this one, due this one, this one, this one, and this and this, so that is only we can write due to this na u 2, due to this u 3, sorry due to this u 3, due to this u 3, between them 3 4, here 1 4, here 2 4, so this all added na, that is the potential energy for system of charges. What is the formula for potential energy, k q1 q2 by r, see that added na, here we can get the potential energy for this system of charges. Yes na. Next see third problem, these are bold important problems, see bold problems, it's not for bold, they are giving in board exam. See here we can write one more problem, see here this is the problem here, see this is initial configuration, x equal to 0 distance, q1 charge is there, that q1 is plus 1 sorry minus 1 microcoulomb, minus 1 microcoulomb. So next one is x equal to 1 distance, q2 is there, that is plus 1 microcoulomb, plus 1 microcoulomb. See x equal to 2 distance, we can arrange q3 charge. What is the change in potential while arranging q3 charge at here, it is initial configuration, initial configuration. See we can arrange na, so what happened here, see we after arranging this is the final configuration, see q1 sorry x equal to 0, q1 equal to minus 1 microcoulomb, x equal to 1, q2 equal to plus 1 microcoulomb, x equal to 2, q3 equal to plus 1 microcoulomb. What now question, actually it is the final configuration after arranging, final configuration. See after arranging q3 charge, so what now here, a third charge, problem is this one, a third charge q3 equal to plus 1 microcoulomb is brought from infinity to x equal to 2 distance, where to where, here no charge is there, it is the initial configuration, here what is the potential, only this one is there, u 2 only is there, so we can arrange the q3 charge at x equal to 2 distance, which is bring from infinity to x equal to 2 distance, we have to do some work. What is the work done, what is the change in potential, so that only we find out, find work done by external agent, that only we want to find out. See here, for this is the initial configuration, It is the final configuration. For arranging this configuration, we have to do some work done. What is that work done, or what is the potential energy that we want to find out? So for that, what we can do now here, what is initial configuration, what is the potential, final configuration, what is the potential, final minus initial. So that we can write here, u equal to u final minus u initial. What is now here u? U final is this one. See, in between two, one potential energy is developed. What is that? Q1 Q2, U12 we can write. So means here K Q1 Q2 by, what is the distance here? 1. So 1 only. So due to this one potential developed, that is K Q2 Q3 by, distance is 1 meter. See, next Q1 and Q3 one potential developed. So that is K Q1 Q3 by 2. Why? Because in between them 2, x equal to 2 is there, 0 to 2. So 2-meter distance is there. So that is 2 minus, what is the initial? Here two charges only is there, one potential only developed, that is U12, that we can write K Q1 Q2 by 1. See, K Q1 Q2 by 1. See here, K Q1 Q2 by 1, K Q1 Q2 by 1 cancel. What is the change in potential work done by external agent is K Q2 Q3 by 1 plus K Q1 Q3 by 2. See, K is common now here, so we can write Q2 Q3 plus Q1 Q3 by 2. Here Q1 means minus 1 microcoulomb, Q2 means plus 1 microcoulomb, Q3 means plus 1 microcoulomb. We can substitute here. See here, I write here, K means 9 into 10 power 9. It is fixed value. K value is fixed. See, Q2 means here plus 1 microcoulomb, 1 microcoulomb into Q3 plus 1 microcoulomb. Yes, na? So minus, sorry, plus Q1. Q1 is minus 1 microcoulomb. Yes, na? Into plus 1 microcoulomb. Yes, na? So this is the values. Microcoulomb means 10 power minus 6. Here 10 power minus 6. I write here 1 into 10 power minus 6, 1 into 10 power minus 6. Yes, now 1 into 10 power minus 6. See, plus minus into plus na minus 1 into 10 power minus 6, 1 into 10 power minus 6 by 2. Yes, now see here, see 9 into 10 power 9. See here 10 power minus 6, 10 power minus 6, 10 power minus 12. Here also is there. So we can common. So that we common now here, potential equal to, change in potential equal to 9 into 10 power 9 into 10 power minus 12 into, here 1 into 1, 1 minus 1 into 1, 1 by 2, 1 by 2 we get. See here, u equal to 9 into 10 power 9, means here we can cancel now, here 3 we get, directly I write here minus 3, 1 minus 1 by 2 not 2 minus 1, so 1 by 2. Here see 2 ones 2, 4.5, means u equal to what, 4.5 into 10 power minus 3. It is work done by external agent or potential energy, so that is joules. So what is the work done by external agent, or what is the potential energy is required for arranging Q3 charge at x equal to t distance from the infinity na, that is the potential energy. What is that? 4.5 into 10 power minus 3 joules. Yes, now see last problem we discuss. So this is the answer for this one. See next one. See here three charges is there. One is, it is Q1, it is Q3, another Q3 here is there. Q2, this is Q2. It is here, see, it is the center. So at what distance now this one? 4 meters. It is 3 meters. It is 3 meters. This charge is minus 4 microcoulomb. Mass is 1 gram. Yes, now this charge is plus 2 microcoulomb. This charge is plus 2 microcoulomb. This is the charge of Q1, Q2 and Q3. See what is the problem now here? If Q3 charge is, see once, see if Q3 charge is left from rest. Find the speed of the Q3 charge when it reaches to 0 nearly. When it reaches to 0, 0 means this center point. When it reaches to 0 point, what is the speed of the Q3 we find out. For that, see here, if Q3 equal to minus 4 microcoulombs, release from or left from rest, left from rest, find find speed of Q3, speed of Q3 charge when it reaches 0 nearly, 0 nearly. That is the problem. See here, Q3 charges is there, Q1, Q2, Q3 arranged in different system. This is the initial configuration. Initial configuration, given configuration this one, so it will change as to, so means it will be left from the rest. What happened, it will moving downwards. That case, when it reaches to 0, while reaching 0, what is the speed of the Q3? So that we want to find out. It will be rest, means it has potential energy. While moving now, these two are rest, it is moving, so means both potential energy, kinetic energy is there. So that's why we can take initial mechanical energy which is equal to final mechanical energy. That condition we can take here. See, I write here mechanical energy of initial configuration which is equal to mechanical energy of final configuration. See, final configuration means I write here, it is Q1, it is Q2, it reaches to this point Q3. Here see, while reaching Q3, while reaching Q3, what is the speed? So that one we want to find out. It is the final configuration. It is final configuration. See, it is initial, it is final. See, now initial position now, so all are at rest. So means what is here, between these two, one potential is developed. Between these two, one potential developed. Between these two, one potential developed. But kinetic energy 0. Why? Because all are at rest. So I write here, in between these two, potential developed. That potential is here, I write potential energy formula is K Q1 Q2 by R. So with the sign, so plus is there, we can take plus, minus is there, minus we can take. These two are plus only. So that's why I write K Q1 Q2 by R. R means what? 3 into 3 plus 3, 6 meters. It's not, that's why we can write plus due to this one. So what is the potential developed here? Q1 Q3, K Q1 Q3 by, here see, this 4, this 3 means this distance is what? 5 meters. So I write here 5 plus, so due to this one, so what is the distance here? 5 meters. See, why not 3 4 5, right angle triangle. So that's why. See, what is the potential here developed? K Q2 Q3 by 5. But kinetic energy is 0. Yes, now kinetic energy is here 0. Why? Because all are at rest only. So no kinetic energy. So that equal to, I write here kinetic, initial kinetic energy. What now here? It is 0. Before I write now here, so potential energy plus initial kinetic energy, that equal to final kinetic potential energy, final kinetic energy. So initial potential energy na this one. So kinetic energy 0. So next, final potential energy. This is the final position. After left from the rest, it reaches to Q3. So that case, so in between these two, one potential developed in between these two. So I write here K Q1 Q3 by R, means this is 3 meters. This also 3 meters, means 3 only, plus in between these two. So K Q2 Q3 by distance is 3. In between first and last means K Q1 Q2 by distance is 3 plus 3, 6, plus kinetic energy na half m v square, half m v square. See here, K Q1 Q2 by 6, Q1 Q2 by 6. What we have, this will be changes to this side. I write here K Q1 Q3 by 5 plus K Q2 Q3 by 5. It will changes to here minus K Q1 Q3 by 3 plus K Q2 Q3 by 3. That equal to half m v square. See what we can do now starting. It is the initial configuration. Total system will be rest. Final configuration, it is in motion. it is in rest. So in between them potential energy, kinetic energy is there. Here also potential energy, kinetic energy is there, but kinetic energy is 0. That's why we can take it is initial, final configuration. So but mechanical energy is same. Here mechanical energy what? Here also mechanical energy same. So we can take that concept. Mechanical energy initial, mechanical energy final. Mechanical means initial potential, initial kinetic. Final potential, final kinetic. So we can write initial potential, this one, due to this is the potential, due to this one, due to this one. See, what is the kinetic energy? 0. Why? Because all are at rest. That's why 0. So next one, second configuration. See, it is in motion, remaining will be rest. In between these two, one potential, so that is this one. So in between these two, one potential. In between these two, one potential plus kinetic energy. What is the kinetic energy? This one only have. So half mv square. Half mv square. See this case, we can change this one here. This cancel. Why? Because same quantity is there. This one add. It will be changes here means minus. Here also minus. Sorry, minus. So we can write here half m means here mass is what here 1 gram. 1 gram means we convert into kilogram. So means 10 power minus 3 kg into v square, that equal to k q1 q3. Q1 means here see q1 plus q3 minus, so 4 into 2 minus 8. So minus 8 by, I write here minus 8 by, sorry, here na k common, na we can write first k common, later we can write q1, sorry, q1 q3, q1 q3 by 5, yes na, plus q2 q3 by 5 minus q2 q3 by 3 minus q1 q3 by 3. Yes na, this one. Yes na, see here we can write first. See k means 9 into 10 power 9. Yes na, we know that value. Q1 na plus 2, q3 minus 4. So means minus 8 by 5. Next q2, 2 plus 2 minus 4 means minus 8 by 4 microcoulombs, minus 8 by 5 microcoulombs. Here minus q2 q3, q2 q3, here minus this one, it is plus minus minus 8, here already minus is there, plus 8 by 3 microcoulomb. Here see q1 q3, q1 q3, so plus 2 minus 4 means minus 8, already minus is there means plus 8 by 3 microcoulomb. Yes na, this is we get. See microcoulomb means into here, sorry, yes na, here microcoulomb, this one microcoulomb. See once, one more again, see once q1 microcoulomb, q3 microcoulomb, microcoulomb into microcoulomb, microcoulomb square. Yes na, here also square, here also square. Microcoulomb square means, microcoulomb square means 10 power minus 6 whole square means 6 to the 12. So I can write common. Yes na, see that is, I remove this one. See 1 by 2 into 10 power minus 3 into v square. Here 9 into 10 power 9 into 10 power minus 12 also common. Why? Because micro square coulomb. So means here minus 8 by 5 minus 8 by 5 plus 8 by 3 plus 8 by 3. Micro square coulomb also I write outside. See here minus 3, here minus 3 remove means minus 9. This minus 9 my plus 9 cancel. What we get now here? 9. So v square equal to this 2 it changes to here 9 into 2 we can write. Here see 8 minus minus 8 minus 8 na minus 16 by 5. Here plus 8 now 16 by 3. See here v square equal to 3, 3 means 9 means 3 square we can write 2. Here see cross multiplication 16 3 jar minus 48 80 by 5 into 3 15 we can write. See here 3 square into 2 48 minus 48 plus 80 means plus 32 by 15. Yes na, see v square equal to 3 square into 2, that 32 can be written as 2 power 5. Here 1 by 15. This we can write 3 power 2, 2 power 6 we can write by 15. Yes, now this can be write it as, see now, 2 power 3 whole square. See, whole square here is there, here is there. We can write 3 into 2 square whole square by 15. Yes, now that we get. I write here. Finally, I write here, see, once v square equal to, v square equal to 3, this one, 3 into 2 square, 3 into 2 square, 2 cube, sorry, 2 cube, 2 cube means 8, 3 into 8 whole square by 15. See here, v equal to root of, na, its root means root of 3 into 8 whole square by root 15. Square root cancel, 8 3s are 24, root 15. Root 15 means approximately 4. We can write 4 6 are. Means what is the speed of the charge q now? See, speed equal to what? 6 meter per second. What is the speed of charge q3 while left from the rest and reaching to 0 na? What is the speed? 6 meter per second. Yes na? See here, only once listen here, what na? Q1 Q3 by 5, Q2 Q3 by 5, Q2 Q3 by 5, 3, Q2 Q1 Q3 by 3. See here, Q1 means microcoulomb, 1 microcoulomb, sorry, 2 microcoulombs. Q3 minus 4 microcoulomb means 4 2s are 8 microcoulomb into microcoulomb, microcoulomb square. Microcoulomb square. Microcoulomb square can be write it as what na? 10 power minus 6 into 10 power minus 6. What we get? 10 power minus 12. That's why here I write 10 power minus 12. See, 8 by 5, this one. Later you know, minus 8 by 5, minus 8 by 5, plus 8 by 3, 8 by 3. Here 16 by 5, here 16 by 3, cross multiplication. Yes, na? We can get this one. 16 3s are 48, 16 5s are 80 by 15. So finally we get this one, 3 square into 2, here 32 na. So 32 can be written as 2 power 5, 2 power 5 into 2 power 1 means 2 power 6. The 2 power 6 can be written as 2 power 3 whole square. Why? Because square is there this side, so changes root will come na, that's why. So 3 into 2 power 3 whole square by 15. That only right. 3 into 2 power 3 means 8 whole square by 15. Square changes to this side, root. Root this square cancel, root 15 here, 3 8 are 24, root 15 means approximately 4, not exactly, approximately 4, 4 6 are 24. Means what is the speed of the charge q3 while reaching O point? O na, what is the speed na? 6 meter per second. This is the concept involved in electrostatic potential energy. I think it is very good. So please see my videos and subscribe and share to your friends. Why we are doing these videos now? Actually, who and all in villages is there, for them not going to coaching centers, so that's why for them it is very useful. They will see and write the NEET and the JEE exams, so for them it is very useful. So they also write exams. So while seeing these videos, please see my videos, subscribe my channel and share to your friends. Definitely it is very good content, it is useful to you who and all writing NEET and JEE exam. So thank you.